In the valley of the River Bollin, at Styal in Cheshire, there is a retort house. It does not look like much from the outside. Brick, functional, the kind of structure a Victorian engineer would have described without enthusiasm as adequate. Inside, the cast-iron infrastructure of a coal-gas works installed during the 1820s survives with the particular quality that only things built to be maintained ever develop. Worn smooth in the right places, tight where it matters, still intelligible to anyone who understands what it is. A Quarry Bank Mill installed its own coal gas works during the mill's major expansion in the 1820s. For approximately 130 years, this site produced its own gas, on-site, in-house, on its own terms, lighting its own factory floors, its own mill manager's house, its own streets, with energy it manufactured from coal it purchased, stored in a gas holder it maintained, and distributed through sectional pipework it could service without external assistance. The national grid did not serve Quarry Bank. The Quarry Bank served itself. This is not a historical curiosity. It is a working lesson in what energy independence actually looks like when the engineering is done correctly. The gas works at Quarry Bank was not a temporary measure. It was not a stopgap pending the arrival of a town supply. It was a deliberate, engineered decision to build a system with sectional pipework, accessible valves, and modular components that could be maintained by anyone with the right knowledge and the standard tools to apply it. That decision held for 130 years. Neither retort house and gas holder tank survive on the Styal Estate today, preserved by the National Trust as part of what the Council of Europe has identified as the most complete and least altered factory colony of the Industrial Revolution. Complete, least altered. Both of those qualities are worth examining carefully, because a gas works that survives intact is not a building that has been preserved. It is a system that was designed to last. This is a story about pipe unions. It is also a story about coal, retorts, cast iron, and the particular clarity of purpose that characterizes engineers who have decided in advance that every component of a system should be accessible, replaceable, and serviceable in the field without specialist intervention. But it begins with the pipe union. Because the union joints fitted at approximately 20-foot intervals throughout Quarry Bank's gas distribution system are the detail that explains everything else about how this installation lasted 130 years. A union joint is not technically sophisticated. It is a connection designed to be broken and remade cleanly, without cutting the pipe, without disturbing the adjacent run, without requiring more than the tools a competent gas fitter would carry, as a matter of course. Its presence at regular intervals in a distribution system is not an accident. It is a statement of intent inscribed in iron and threaded into the fabric of the building. This system was not designed to be replaced section by section when something failed. It was designed so that something failing was a manageable event rather than a crisis. Before we continue, a brief interruption, which is more than this mill has had in the last 2 centuries. If you find value in documenting the things that were built to last, the decisions, the specifications, the engineering principles that made longevity possible, consider subscribing. And this channel exists because someone should be paying attention to these systems before the last person who knows how they work retires and takes the knowledge with them. And if you have worked on something like this, maintained it, repaired it, sourced parts for a system whose manufacturer ceased trading before you were born, tell us in the comments. What was it? How long had it been running? What did it take to keep it that way? We are genuinely interested. Unlike most comment sections, this one occasionally contains useful information. Now, back to the mill. The technology that lit Quarry Bank Mill had been demonstrated to work on an industrial scale fewer than 20 miles away. In 1805, William Murdoch, a Scots engineer employed by Boulton and Watt, installed the first large-scale coal gas lighting system in a working textile mill. The mill was Phillips and Lee's operation in Salford. The installation lit the mill's workrooms and courtyard from gas produced in iron retorts, stored in a cast-iron gas holder, and distributed through sectional pipework. It worked, and it worked sufficiently convincingly that within a decade, the engineering template, retort bench, condenser, lime purifier, gas holder, distribution main, had been established well enough to be supplied as a complete package and erected by competent local men. Samuel Clegg, who had trained under Murdoch and later became the first engineer at the Gas, Light and Coke Company in Westminster, introduced two refinements that made private gas works of this kind genuinely maintainable: the hydraulic main, which provided a simple means of drawing off tar without interrupting gas flow, and lime purification, which removed the sulfurous compounds that made early coal gas unpleasant and corrosive to fittings. By the early 1820s, the process was understood. The components could be specified. A mill, the scale of Quarry Bank, could install a gas works with reasonable confidence in its reliability, provided the installation was done correctly and the subsequent maintenance was taken seriously. The Greggs took both seriously. Samuel Gregg's mill had already, by the 1820s, established a record of engineering decisions made on the basis of long-term function rather than short-term economy. The water wheel, a 32-foot diameter machine by Thomas Hughes, capable of the power equivalent of approximately 120 horses, had been built with maintenance as a design consideration. The mill buildings themselves were constructed to a standard that, 2 centuries later, they are still standing in. When the decision was made to install a gas works during the major expansion of the 1820s, it was made in that same tradition. The town gas supply that would eventually reach Cheshire had not arrived, and even when it did, connection to a public utility meant dependence on external pricing, supply reliability, and the institutional continuity of an organization whose interests were not identical to the mill's. On-site production eliminated that dependence entirely. The gas works at Quarry Bank was therefore not an improvisation. It was an informed engineering decision by owners who had a demonstrated preference for systems they could control and maintain. The coal gas works at Quarry Bank, in its 1820s configuration, was a compact but complete system, modest in scale by comparison with the town gas works, not modest in the quality of its engineering thinking. At its heart was the retort house. The retorts themselves, horizontal cast-iron vessels, each sealed at both ends, were set into brick furnace benches and fired from below. Coal, charged into the retorts by hand, was heated in the absence of air. The carbonization process drove off the coal gas along with a range of undesirable companion vapors: coal tar, steam, ammonia, and the hydrogen sulfide that made early coal gas smell as though it had arrived from somewhere the ventilation was poor. The crude gas from the retorts passed first to the condenser, a run of cast-iron pipes, cooled by air or by a water jacket, through which the heavier tars were condensed out and drained into a tar pit below. The tar was not wasted. In a working estate such as Styal, there was always a use for a material that could preserve timber, seal stone, and discourage rot with equal competence. From the condenser, the gas entered the purifier, a vessel containing hydrated lime or iron oxide, through which the gas passed in contact with the purifying material. The hydrogen sulfide was absorbed. The gas emerged measurably cleaner and considerably less offensive. The purifier required periodic replenishment as the active material became saturated, a task that was dirty, regular, and entirely manageable, provided the access hatches were accessible. They were. The access hatches were designed to open. From the purifier, in the cleaned gas passed into the gas holder, a cylindrical vessel sitting in a water-sealed pit, the vessel itself floating on the surface of the water and rising or falling with the quantity of gas stored within. The principle was straightforward. The gas exerted pressure on the underside of the floating vessel's crown. The vessel rose. Gas was available for distribution. The water seal prevented leakage at the base. The mechanism required maintenance of the water level and periodic inspection of the guide framework, but it did not require sophisticated instrumentation or specialist knowledge. It required attention. The distribution system ran from the gas holder through cast iron mains to every part of the mill that required lighting. The pipe unions at 20-foot intervals were part of this system from the outset. So were the serviceable burners at each gas point, fittings designed to be removed, cleaned, and replaced by a person with a set of basic tools and the understanding to use them. The design did not assume the system would never need attention. It assumed attention would be required and arranged accordingly. The original instruction manual for a gas works of this period recommended cleaning the condenser quarterly and replacing the purifier material as required by smell. The smell test remains, to this day, one of the more reliable diagnostic methods ever applied to a gas purification system. It was considered sufficiently precise to be the standard for approximately a century. A gas works of this type operated on a maintenance cycle that the workers of the 1820s would have established, and the workers of the 1950s would have inherited with most of its practices intact. The retorts required charging and emptying at intervals governed by the rate of gas production demanded by the mill. The furnace required stoking and ash removal. The condenser pipes required periodic clearing of accumulated tar deposits. The purifier required fresh material on a schedule announced not by a calendar entry, but by the smell of the gas in the distribution main. And the gas holder required inspection of the water seal, checking the water level in the pit, and periodical attention to the guide mechanism that kept the vessel rising and falling true. None of this was technically demanding. All of it required someone who knew what they were doing, that someone existed at Quarry Bank across the full operational life of the works. The knowledge was not written in a manual that outlived its readers. It was passed from the engineer or contractor who installed the system to the mill's own mechanics and stokers, and from them, over decades, to the workers who succeeded them, from those workers to the next men in the role. The maintenance chain ran through the Styal workforce without documented break. What was replaced over 130 years tells its own story. The retorts required replacement on a cycle of years. Cast iron in continuous service at carbonization temperatures eventually fatigues, distorts, and begins to leak. Replacement was routine. The retort bench was designed to accept it. When the purifier material was replaced on a rolling basis throughout the operational life of the works, the gas holder's water seal required topping, and its moving parts required lubrication and inspection. What was not replaced was the pipe distribution system. The cast iron mains, jointed at 20-foot intervals with union connections, ran throughout the mill's operational life without requiring wholesale renewal. The individual joints could be broken and remade. Sections could be isolated and serviced. The system could be partially drained and partially repressurized without taking the whole out of service. The design was not cautious. It was confident. Confident that the people maintaining it would know what they were doing. Confident that the tools required would be available. Confident that a system built accessibly and maintained regularly would not require the kind of emergency intervention that systems designed with replacement in mind invariably create. That confidence was justified for 130 years. The story of Quarry Bank's gasworks is not, in the strict sense, a story about a near-miss retirement. It did not require saving by a last-minute procurement decision or an engineer's well-timed argument at a board meeting. It worked until the mill stopped needing light, at which point it stopped. What it is a story about is a distinction that matters, the difference between a system that is decommissioned and a system that is rendered obsolete. Through the 19th and 20th centuries, every private gas works in Britain faced the same question in different guises: connect to the public supply or continue independent production. The public supply won, as utilities generally do. Not necessarily because the engineering was superior. A well-maintained private works was reliable by any reasonable measure, but because the economics of a shared distribution network once built out, made external supply cheaper than on-site production for most applications. Most mills made the connection when it became available and economically compelling. Quarry Bank's position on the Styal Estate, a deliberately self-contained industrial community set apart from the surrounding towns by design and by topography, meant the connection arrived later, and the calculus remained in favor of on-site production for longer. The gas works was not maintained out of stubbornness. It was maintained because the alternative was a worse outcome. That clarity was its own maintenance culture. The people charged with keeping the system running did not do so with an eye on history. They did so because the factory floors required light, the mill manager's house required light, and the streets of Styal required light. The gasworks provided it. The maintenance cycle continued because the consequence of not continuing was darkness. The retort house and gas holder that stand on the Styal Estate today are the physical remnants of a system that operated in that frame of reference from the 1820s to approximately 1950. They were not preserved, and they survived because they were well built and then left standing. That too is an argument. The gas holder at Quarry Bank stands on the Styal Estate, within the grounds that the Council of Europe identified as the most complete and least altered factory colony of the Industrial Revolution. The retort house stands with it. These are not ornaments. They are evidence. Evidence that a mill built in 1784, before the steam engine was the dominant power source, before public gas supply existed, before the national grid was imaginable, made a series of engineering decisions that sustained its own energy independence for 130 years. The decisions were not complicated. They were the same decisions this channel returns to, subject after subject, machine after machine. Design for access. Build for maintenance. Choose the component that can be replaced by a competent person with standard tools over the component that requires specialist intervention or the manufacturer's attendance. Pipe unions at 20-foot intervals. Retorts arranged for straightforward charging and cleaning. A gas holder that operated on the physics of a floating vessel and the maintenance requirements of a water seal. A purification system that told you when it needed attention by the simple mechanism of making the gas smell worse. Feedback loops, access panels, replaceable components, common tools. These are not revolutionary ideas. They were not revolutionary in the 1820s. They are, however, ideas that the design culture of the late 20th century progressively set aside in favor of systems that could not be maintained by their users, that depended on proprietary components, and that were designed with replacement in mind from the first drawing. Quarry Bank Mill's gas works did not need to be replaced. It was simply, eventually, no longer needed. That distinction matters more than it might at first appear. The mill is still there. The retort house is still there. The gas holder tank is still there. They will still be there tomorrow. If this subject interests you, and we suspect it does, since you are still here, subscribe to the channel. There are more machines, more systems, more decisions made by engineers decades ago that are still quietly paying off today, largely unnoticed by everyone except the people keeping them running. And if you have a connection to what we have just described, a system you maintained beyond all reasonable expectation, a repair that should not have worked but did, an infrastructure decision made by someone now forgotten that kept something going for decades longer than anyone planned, tell us in the comments. And the engineering knowledge that kept these systems alive was never written down in a form anyone thought to preserve. It lives in the people who learned it from the people who built it. We would like to hear from them before they stop answering questions.